Welcome to our channel. In this lecture, I will explain the practical transformer is operating under load condition. So practical transformer operating on load condition. In an examinations, he will ask, explain the operation of a transformer, practical transformer operating under load condition, and this is also called as a MMF balancing on load. So I am taking a core type of transformer. Here I am drawing a core type of transformer. On the limb 1, I am wound the winding, that is a primary winding. On limb 2, we have to wound the winding, that is called the secondary winding. So this HV winding has a N1 number of turns. This LV winding has N2 number of turns. So from the previous lecture, if you draw the phasor diagram, the angle between supply voltage and the magnetizing component of current is 90 degrees. The wattful component of current is in phase with the supply voltage, that is called the active component of the current. So by adding these two vectors, I am getting a no load current, and the angle between the supply voltage and I0, the angle between supply voltage and I0 is called the phi naught, where phi naught is called the no load power factor angle. No load power factor angle. So this is the flux, and the angle between the flux and induced EMFs is 90 degrees. So this is from the previous lecture I have posted here. Whenever sinusoidal voltage is given to the transformer primary winding, an alternating current is flowing through transformer primary winding, which will produces an alternating flux, and this flux will be links with the primary winding and secondary winding according to Faraday's law of electromagnetic induction, and EMF is induced in a primary and secondary. If the transformer is operating under no load conditions, the current drawn from the transformer is I0, that is called the no load current. What is I0? Is called the no load current. Once it has been loaded, the load switch is closed, what will happen? The current is flows through load, and the number of turns N2 also. The I2 is flows through load, and the number of turns N2, and this is the current direction during a positive off cycle. The terminal voltage, we can say that the voltage across the load is V2. When the current flows through a load, which will produces a secondary MMF. What is MMF? MMF is the magnetomotive force and the number of turns into current. With this secondary MMF, which will produces a secondary flux, where phi 2 is called the secondary flux. This secondary flux will opposes the main field flux. So this is the flux direction at a particular instant, that is during positive off cycle. The flux which is produced by the load which is in opposite direction, then the net flux will be decreases phi minus phi 2. Because of this, EMF is directly proportional to flux. Why? Because E is equal to 4.44 into phi m into F into N1 or N2. The EMF value will be decreases E2 minus V2. This drop increases. E2 minus V2 is called the drop, and the primary voltage is V1 and the induced EMF is E1. If the winding has a resistance, then this current is called the primary current. If E1 is decreases, E1 value will be decreases, then V1 minus E1 will be increases. Let us assume under no load condition, the supply voltage is 230. The transformer induced EMF is this is 232. You can assume that 232. This is 230 volts. The induced EMF is 230, and the resistance of the winding, primary winding, let us assume it is a 1 ohm. Then I naught is equal to 232 minus 230 divided by 1. That should be equal to 2 amperes. This is under no load condition. Generally the voltage is not a 232, but what I want to convey is what is the difference between the no load current and full load current. Because of flux reduction, the EMF induced in a primary winding and secondary winding both will be reduces. Now E1 is reduces to 220 volts. This is called the case 2, and the supply voltage is constant, that is called the 232 volts. Now the I1 is equal to 232 minus 220 divided by the resistance of the winding is constant, that is 8 amperes. See here, if the induced EMF in the primary winding decreases, the V1 minus E1, the drop will be increases. The current drawn from the transformer increases. It will draw the additional current, that is called the I2 dash. This is a phasor, both are phasors only. Now the resultant current is I1. So for a lagging load, if I am taking the E2 and V2 both are is in same phase, by neglecting the small angle, for a lagging load, the load current I2 is lagging at an angle of phi 2. For a leading load with respect to V2, I2 is leads at an angle of phi 2. Okay, here it is a phi 2 is called the secondary flux, but here this phi 2 is called the phase angle, secondary phase angle. Okay, so I am drawing the phasor diagram for lagging power factor. If it is a in phase means, V2 and I2 both are is in same phase. The angle between the voltage and current is in 0 degrees for a resistive load. So once again I am drawing the phasor diagram. This is V1. The magnetizing component of current is like this, is lagging by 90 degrees. The induced EMFs in a windings is also lags by 90 degrees. By neglecting the small angle, the V2 is also, let us assume the V2 is in phase. With respect to V2, the I2 current is lagging at an angle of phi 2, where phi 2 is called the secondary power factor angle. IW is in phase with the supply voltage. So this is called the no load current I naught. See, I naught is a phasor sum of magnetizing component of current and wattful component of current. But the primary current I1 is a phasor sum of no load current plus reflected coefficient of secondary current. This I2 dash is called the secondary reflected current. Secondary reflected current. So project exactly, it is 180 degrees to I2. It is a reflected current. So this is a line. So I am drawing with the different colors. So this is called the I2 dash. By adding these two vectors by using a parallelogram concept, then you will get the resultant current. So draw a line which is parallel to I naught. The length of this one is I naught. Draw a line from this I naught, which is parallel to I2 dash. Then I am getting the resultant current. That resultant current is called the I1. The angle between V1 and I1, the angle between the V1 and I1 is called the primary power factor angle. The angle between the V1 and I1 is called primary power factor angle. The angle between V2 and I2 is called secondary power factor angle. This is for the lagging power factor of the phasor diagram. So once again, listen, when the secondary is loaded, the secondary current flows through a load and as well as the secondary number of turns. It will produce a secondary MMF, which in turn develops a secondary flux, which will opposes the main field flux, and the net flux will be decreases. The EMF which is induced in a primary winding and secondary winding, both are decreases. It will primary draws the additional current. Primary draws the additional current that is produces phi1 dash, which is exactly equal to phi2. Once phi1 dash and phi2 are equal and opposite, then both are nullified and the flux in the transformer core is always constant. Now N1 into I2 dash is equal to N2 into I2. That means phi1 dash is equal to phi2. The flux in the transformer core is always constant. So I2 dash is equal to N2 by N1 into I2. So that's why I got it as, what is N2 by N1? N2 by N1 is transformation ratio. So K times of I2, where I2 dash is equal to K times of I2. And here I2 dash divided by I2 is equal to N2 divided by N1. That should be equal to E2 divided by E1 is equal to K. So cross multiplied EMFs and currents, E1 into I2 dash is equal to E2 into I2. So what is I2 I1? I1 is a primary current. I2 dash plus I naught. I1 bar is equal to I2 dash bar plus I naught. So by neglecting the no load current, E1 I1 is equal to E2 I2. This is called the primary side kVA. So primary side kilovolt ampere is equal to secondary side kVA. So now the transformer definition is satisfied. Transformer transfers electrical energy from one side to another side. So transformer is also called as a constant power device. So the primary side kVA is approximately equal to secondary side kVA. So that's why the transformer is a constant power device. And once phi1 dash is equal to phi2, if both are nullified, then the flux in the transformer core is always constant. Suppose 100 milliweber are there, that is called the main field flux. The phi 2 value will be, let us say, 10 milliweber. Based on the load it will be, it based on the load the flux value will be changes. And now the net flux will be 90 milliweber because of it draws the additional current plus 10 milliweber will be added. Then the net flux in the transformer core is always 100 milliweber. Maybe 1 or 2 percentage will be changes in the flux, but the flux in the transformer core is always constant. That's why the transformer is also called as constant flux device. Subscribe my channel, like, share and subscribe. Thank you.